Okay, calculus fans, we are back with section 5.5, and this is part 2. So we're still working with the substitution rule, and what we did last time is we talked about indefinite integrals. That was part 1. So part 2 we talk about definite integrals, and there are 2 methods for handling these, and they're related. I'm going to show you both of them, and you can choose whichever one you want. It doesn't matter. They both work on every problem. Sometimes when we have really messy problems, one way will be better than the other. But generally speaking, for most problems, it's just whatever your personal preference is. So I'll show you the first method, which we will call method 1, I suppose. It doesn't really have a name like this, but we'll just call it method 1, method 2. Method 1 says this: transform the integral and the limits of integration. So we transform the integral just like we did in the first video. We transformed the integral using u-substitution, but now we also have to transform the limits of integration. Okay, so this we'll call method number 1. So as an example, we'll just do this example twice, one with each method. So let's say we've got this definite integral from -1 to 1 of 3x squared times the square root of x cubed plus 1 dx. And remember, wherever you see this integral symbol, there's a d something, right? Whatever the independent variable is. Once we integrate and that goes away, the dx goes away also. Okay, so for this one, if we just were looking at this problem and wondering about how to integrate, we could look on our sheet of integrals and we would see that this is not on there. So we want to think about u-substitution, and again we want to think, is there some like inside function that I can take the derivative of, and that derivative or multiple of it also appears? And that is the case here. So if we let u be this inside function, this function underneath the radical, right? If we let u be x cubed plus 1, then du is going to be 3x squared dx. And look how lucky we are. 3x squared dx is right there. So we can get rid of the 3x squared dx and replace it with a plain old du. And then this, of course, is square root of u. Okay. So we could say, all right, this thing is the same as square root of u du. But here's where the problem comes in. This original integral involved x, right? X, we're integrating as x goes from -1 to 1. So now I have a new integral in terms of u, not in terms of x anymore. So I can't put -1 to 1 because this was specific for x. Think of this as this integral could represent the area under the curve of this function between -1 and 1. Now we've got a different function, right? This is different than this function. So I can't still go from -1 to 1. So what we do is we go back to our original u substitution, because this gives us a relationship between x and u. So I'm going to use this and say, okay, what happens when x equals -1? What will u be? And then also, what happens when x is 1? What will u be? So I'm going to go back to this, and I'm going to say, okay, if x equals -1, u equals -1 cubed plus 1, which is -1 plus 1, which is 0. So when x is -1, u is 0. See, all I did is I went here, I let x be -1, I plugged a -1 in for x to figure out what u is. All right, so if x is -1, u is Negative 1 cubed plus 1. Negative 1 cubed is negative 1 plus 1 is 0. So we're transforming the integral, and we're also transforming the limits of integration. All right, that's method 1. So we've got this negative 1 becomes 0. And now I do the same thing for when x is equal to 1. So then I come over here. Same thing. I say, okay, what about if x equals positive 1? Well, then u will equal 1 cubed plus 1, which is 1 plus 1, or 2. So my new upper limit of integration is 2. And again, all we're doing, we're using this substitution that we came up and letting x be 1 in this case. So we have a brand new problem, but the answer is the same. This answer is the same as this answer. And now here's the thing. Once we change everything to u, including the limits of integration, we never go back to x. We just answer this question, treat this like a brand new problem because it's equivalent, it's the same answer. Treat this like a brand new problem and see what happens. So if we had this problem, we would say, okay, I'm going to write this as u to the 1/2 du. So if you integrate that with the power rule, 1/2 plus 1 is 3/2. So you have 2/3 u to the 3/2 from 2 to 0. Right, because this goes up by 1. So 1/2 plus 2/2 is 3/2. Then you divide by 3/2, which is like multiplying by 2/3. Now I plug in a 2. So I have 2/3 times 2 to the 3/2 minus 2/3 times 0 to the 3/2, which of course is just 0. So really we get 2/3 times 2 to the 3/2, which we don't want to really leave 2 to the 3/2 because remember we did this before, something like this. 2 to the 3/2, you can think of it as 2. I guess this one would probably be easiest to think of it like this. Let's split it apart this way. 2 to the 2/2 times 2 to the 1/2, right? Because if we've got a number raised to more than 1, we can write it as 1 and then plus whatever's left. So 2 to the 3/2, I could make this 2 to the 1, 2 to the 2/2, then it leaves me with this. And then that's just equal to 2 to the 1, which is 2 times the square root of 2. So this becomes 2/3 times 2 times the square root of 2, which gives us an answer of 4/3 times the square root of 2. So this would be our answer. Okay, so with this method, just a quick recap here. We transform the integral just like we did before, and we transform the limits of integration. Once we do this, we never go back to x. See, once these limits are changed, then we never go back to x. There's no reason to go back to x. We have an equivalent question that we can answer. Okay, so that's method number 1. So method number 2, we're going to do it a little differently, but we should get the same answer. And then you guys can pick which method you like best. But this is method number 2. So we'll say method 2. Okay, so here is method number 2. Well, we're going to transform the integral just like before, but now this time we're not going to change the limits of integration. What we're going to do is we're going to use what's called dummy limits, which I'll explain when we do one, but we're going to integrate with these dummy limits. Then once we're done integrating, we're going to change back to x. Now I put x here because normally our independent variable will be x, but basically change back to whatever the original variable was, and then you use the original limits. Okay? So we'll look at the same problem, and it starts off the same way. We're just going to use u-substitution. So we go ahead, u equals x cubed plus 1. du equals 3x squared dx. And then we notice that's exactly what we need, 3x squared dx, 3x squared dx. So we can substitute. So we would go the square root of u, and then we've got du, right? So just like before, 3x squared dx, that's just du, and this is the square root of u. Now here's what we're going to do differently. What we're doing now is we're saying, well, I know that these limits of integration are going to change, right? Because I changed from x to u, so I know these will change, but I don't care what they are. I'm not going to take the time to find them. I'm going to put these dummy limits in here. That way I can put an equal sign here. I'm putting these dummy limits. If I put -1 in one, I'm almost certainly it's going to be wrong. And even if you change them back, it just looks sloppy. And someday you guys are going to be getting paid the big bucks to not be sloppy, to be very detail-oriented. And so let's just get in good practice now. We're going to just say, I don't know what these are, and it doesn't matter because I'm going to change them back. So I'm going to use A and B here or something just to show that they're different, but I don't know what they are. These are called dummy limits. And then from there, you just integrate like you normally would. So we have a to b, u to the 1/2 du. And we just go ahead and integrate, so that gives us 2/3 u to the 3/2 from b to a. And now at this point, what I'm going to do, once I've integrated, so see I integrated with dummy limits, now I change back to x and use the original limits of integration. So I'm going to change all this back. So now I'm going to have the answer is 2/3 times u, which is x cubed plus 1 to the 3/2, and then from -1 to 1. And once we do this, you'll see in a second here, once we start plugging these limits in, we're going to go through the exact same math as we did in the previous problem. Because watch what happens when I plug the 1 in. Okay, so I plug the 1 in, I get 2/3. 1 cubed plus 1 is 2 to the 3/2. Right, once I plug the 1 in here, I get 1 cubed plus 1, that's just 2 to the 3/2. And then you go minus, fundamental theorem of calculus says minus, and now I plug this in. So remember, it's this minus this. So you plug that one in, and we're going to get 2/3. And now I'm plugging the -1 in here. -1 cubed is -1 plus 1 is 0, so you get 0 to the 3/2. And you can see we get exactly the same math. 2/3 times 2 to the 3/2, which we said is 2/3 times 2 times the square root of 2, which we said is 4/3 times the square root of 2. So we get the same answer, and it really is just a personal preference. Either one of these methods is fine, and you're always going to be able to pick. I'm not going to say use one method or the other. And this method 1 and method 2, though, they don't have names for them. They're just very common. And you can choose whichever one you'd like. So here's another problem, number 60. And once again, I'll do this both ways. Every time I've ever taught calculus, I've always taken a vote after you do a few of these. And I would say it's pretty close overall. Through the years, it's been really close, but probably most students prefer not using dummy limits. Now, it could be because I always teach that method first. And one thing you learn if you're in education long enough is typically the first way you learn something, you're convinced that's the best way. And especially the older you get, like the older you are, the more you're convinced that the first way you learned it is the right way. So that could be it. There could be some bias here because I always teach that method first. But it's pretty close. I would say not exactly half. Maybe there's a slight edge towards the first method, but there's definitely a lot of people like the second method too. So for this problem, I'll do both methods again. And then after that, maybe I'll just do the first method because, like I said, it's a little bit more students do it that way. But what you should do right now is try this problem first and then come on back and see if we agree. So for this problem, if you look at this, you're going to see that is not on the sheet of integrals. And I know I keep saying that because I want us to get used to that idea of is this a known integral? And if not, we have to see if we can tweak it to turn it into a known integral. So it's definitely not on there. So then we want to look for some kind of function where if I take the derivative of that function, its derivative is also here somewhere, a multiple. And especially if it's like an inside function. So like right here, we could maybe think of this. What if we let u equal negative x squared? Then this would be like e to the u, right? And we know the antiderivative of e to the u with respect to u is really easy. That's just e to the u. So if we have our u substitution, u equals negative x squared, then du would be negative 2x dx. And of course, we don't have, let's see, we don't have that. We've got x dx. So we can fix that easy enough. Let's multiply each side by negative 1/2. We get negative 1/2 du equals x dx. So then we can substitute these out. So that will give us, oops. You get negative 1/2, we'll just put out here. And we would have e to the u du. And I'll go ahead this first time. Let's change these limits. It gives us a little practice anyway. So remember, the reason we're changing this is because this integral is in terms of x. So we're looking at this integral as x goes from 0 to 1, all right? So now that we changed it to u, we need to find new limits of integration here. So we go back up to here. We go back here, and we say, what happens when x is 0, and then what happens when x is 1? So if we come back over here, and we just say, okay, I'm going to let x equal 0. And when you do that, u would be negative 0 squared, which is 0. And then we let x equal 1. And when we do that, u would be negative 1 squared, which is negative 1. Because look at what it's saying. U is negative x squared. It's not negative x in parentheses squared, right? It's negative x squared, like the opposite of x squared. So if x is 1, the opposite of 1 squared is negative 1, right? So be careful with this right here. We're not squaring the negative 1. We're squaring the x, right? And then taking the opposite of it. So then we've got our new limits of integration. So 0 is 0, 1 is negative 1. And if you've done integration for a while, you see this looks a little weird because normally you have the higher number here and the smaller number here. And a lot of times, if you look at a problem like this in the book, they'll switch these around. They'll put the negative 1 down here and the 0 up here. And when you do that, the sign changes. So you don't have to do it, but it does make it a little easier to work with. Remember, we had that example where we had, when we were talking about how these properties of integration, the properties of an integral, we said that we could switch a and b to b and a. And as long as you put the negative sign there, then they're equivalent. So you can swap these limits of integration. You get the same number, just the opposite sign. So what we could do here is just go from negative 1 to 0, and we'll have a positive 1/2 e to the u du. So then we integrate, and this one is an easy integral, right? So you integrate, and we're going to get 1/2 e to the u from 0, or from negative 1 to 0. And remember the thing here, if we do this, we're not going back to x's, right? We don't go back. If we change the limits of integration, we don't go back to x's. There's no reason to. We can just integrate We've changed everything. We integrate here, so we're going to get 1/2 e to the u minus 1/2 e to the minus 1. Actually, this is e to the 0, not e to the u. 1/2 e to the 0. Well, e to the 0 is just 1, right? So this is going to be 1/2 times 1 minus 1/2 e to the minus 1. And from here, there's a lot of different ways you can write this. I'm not sure how Stuart would do this, but they might factor out a 1/2 and go 1 minus e to the minus 1. They could maybe do something like this, 1 minus 1 over e, right? Because e to the minus 1 is 1 over e. Any of these are fine. However you want to finish it from there is okay. And then I'm just going to walk through this again, but this time using the dummy limits, just so you can see the difference. So the integration is pretty much the same. We start off, we say, let's let u equal negative x squared. So then du is going to be negative 2x dx. And we know over here we've got x dx, so we need to get rid of the negative 2. So we multiply each side by negative 1/2. And that will get us the x dx, which is what we need. So then we can do our substitution. We get rid of the x dx and swap it out with negative 1/2 du. And this becomes e to the u. So we would go, this is equal to, oops, let me move this over a little bit here. This is equal to negative 1/2 e to the u du. And again, I'm doing some things in one step where we used to do two. So this negative 1/2 multiplier can just come out front. And now what we're going to do, we're not going to change these limits, right? We're just going to say, you know what, I don't know what they are, but they are almost certainly are not 0 and 1 anymore. So I'm just going to put these dummy limits in here. And now I'm just going to integrate this. And I'm going to integrate this and get negative 1/2 e to the u from b to a. And now that I've integrated, I'm going to put everything back. That gives me negative 1/2 e to the negative x squared, and put the original limits of integration back, which were from 0 to 1. This is supposed to be a straight line here. And just like last time, the algebra, once we plug this in, or the arithmetic, will be the same as before. So we plug in the 1 for x, then we go minus, so we plug the 0 in for x. So that will give us negative 1/2 e to the negative 1 squared minus 1/2 e to the 0. And again, be careful up here. It's not negative 1 in parentheses squared. It's negative 1 squared, right? Just do order of operations. If you plug this in your calculator, you calculate it with the order of operations, and it will tell you this is negative 1. So we end up with negative 1/2 e to the negative 1 plus 1/2, right? Because right here we've got minus, which, as you guys have taught me, is a giant plus. And then from here, we can, rewrite it however you want to. If you want to make it look like we had before, we could go like this. And we could factor out the 1/2. Again, you don't have to, but you can see how you get, oops, it's a negative 1. 1 minus 1 over e. And again, any of these are fine, really. Once you get here, this is all good, all these. However you want to do it, they are all just fine. There are a couple special cases that we should probably be aware of, and they don't really come up a lot. But the reason that I mention this is because when I first started teaching, students would always ask me about things they were seeing in the student solutions manual where they seemed to be skipping steps. And the solutions manual kept making use of these symmetric functions. So I always mention them now because they come up occasionally, and one in particular makes life a lot easier to use. So basically, if they have these symmetric functions, so This will go back to maybe an algebra class when you talked about the symmetry that even or odd functions have. So I'll review a little bit too to kind of refresh your memory. But suppose we have this continuous function. Suppose f is continuous on this interval from negative a to a. It's like maybe negative 4 to 4 or something like that, where these are the same number, but one's negative. Then two things could happen. If n is even, so an even function would be something like y equals, I'm going to do a different color here, y equals x squared. So y equals x squared, of course, looks like this. Even functions are functions that have symmetry with respect to the y-axis, or y equals cosine of x, right? That's the even function. There's a symmetry with respect to the y-axis because cosine is, goes something like this. It goes through at negative pi over 2 and pi over 2. So even functions have the effect that when you put a negative input into the function, you get the same as if you put a positive input in. So like if I plug a negative 3 in here, I get a 9, same as if I put a positive 3. So like f of negative 3 is the same as f of 3. So when you have functions like that, they're said to be even, and they are symmetric with respect to the y-axis. So when that happens, this is easy to see why this would work. So let's say I'm going to integrate this function y equals x squared between, say, negative 1 and 1. Well, we can see that because of the symmetry here, these are the same. So instead of integrating from negative 1 to 1, I could just integrate from 0 to 1 and double it. So if you've got an even function, usually this is easier because usually plugging a 0 in is easier than plugging a negative number in. So every once in a while, this will come up, and you can make life easier by doing this. If you don't, honestly, a lot of times you won't even notice it. So you just go through and plug in negative a to a, you get the same thing. But if you happen to notice it, it saves some time. And the people who write the student solutions manual, they notice it all the time. So whenever it's possible, they'll do it. So you may see this if you look in the solutions manual. If you're stuck on a problem, they apparently do this quite a bit. And then if you've got an odd function would be like y equals x cubed. So it goes like this. If you're wondering, does it have anything to do with an odd function that's an odd power? Yes, it does. Because even powers will be even functions and odd powers will be odd functions. And I'm talking about like real basic problems like y equals x to the fourth. So, to have this kind of symmetry, if you tweak them at all, they won't work like this. But things like y equals x cubed or y equals sine of x, where sine has this, these are said to have symmetry with respect to the origin, which basically means if you were to take this and rotate it around the origin 180 degrees, you can't tell, right? If you spin this around 180 degrees, it looks just the same. So they have symmetry with respect to the origin, and then you can see why this would work. If you integrate, the sine function between a couple of points here, between maybe this point here and this point here, well, this is going to give like a negative number. This will give a positive number, so that when you combine them, you get 0. So these are just a couple of things. They're not huge. They're not giant time savers, but they will save time if you notice them. So just wanted you to be aware of those. Okay, and then we've got a problem that looks like an easy problem. This looks like it would be on our integral sheet, right? We've got one for sine and cosine, but this one actually is not on there. It seems kind of simple, but it's not quite as simple as it looks. But it isn't too bad of a problem. And now that we know how to do u-substitution, we can actually integrate tangent. So the way we do this is we rewrite this as sine of x over cosine of x. And at this point, we can use u-substitution. So if we let, let's say, let u equal cosine of x, the reason I choose this is because then I'm going to eventually get 1 over u. And we know the integral of 1 over u. That's the natural log of the absolute value of u. So if we let u equal cosine of x, then du will be negative sine of x dx. And then if you look at this problem, if I change this a little bit, right, so this is equivalent to this, because if you multiply, this would be like sine of x over 1, and we multiply fractions, you go straight across, so we would get back here. So we've got almost what we need. We need sine of x dx. We've got negative sine of x dx, but we could multiply each side by negative 1 and get negative du equals sine of x dx. And at that point, we have exactly what we need. So now we can do our u-substitution. So we would get 1 over u du, and the negative we can just bring out here. So when we integrate this one, we end up with negative natural log of absolute value of u plus c. And of course, when we re-plug in or resubstitute, we get negative natural log of cosine of x plus c. So this integral right here, in the bad old days before we had graphing calculators and all this awesome stuff to help us out with and do way more interesting problems, we had tables of integrals, and that was all we had. So you'd look in a table of integrals to see if you could find these, and if you looked up this one in table of integrals, you would sometimes see this. But there's another one you could see also, so I'm going to mark this one. And you should probably write this on your table of integrals. There's a couple of them that I add usually at the end of Calc 1. This is one of them. And there's another one in the homework, which is cotangent of x, which is handled very similarly and actually comes out with an easier, it's actually easier than this one. Because this one, you're going to see there's 2 ways to write this one. So this is an answer in some of the tables. But the problem is some people don't like the negative. So here's another way to write this. So as you guys know, there's this rule of logarithms. It says the natural log of a to the b is equal to b times the natural log of a. We talked about it because it allows you to take a power and turn it into multiplication, which is a reduced level of complexity, which is what logarithms do. So in this case, we're going to go the opposite way. So say this b is a negative 1. We could move it up here and have natural log of a to the negative 1. So let's do that here. Let's move this up. Okay, so if we wanted to, we could say, okay, this is equal to the natural log of cosine of x to the negative 1 plus c, right? And then that is equal to the natural log of 1 over cosine of x plus c. And I'm putting every single step in here, which you don't need to, but would you guys agree that 1 is exactly the same as the natural log of 1? And then if you have the natural log of a over the natural log of b, you have the natural log of a over b. And what is 1 over cosine? That's secant. So this is the other way that this one shows up in the tables. And this is kind of a 50-50 thing. Some people like this better because it's positive. Other people say, yeah, but I don't like secant. I'd rather have sines and cosines, so they like this better. Both of these are fine, but you should probably on your integral sheet write write the integral of tangent of x dx and put whichever one of these you like best or both. And then also write the integral of cotangent of x dx, and when you get done with that homework problem, write your answer in there. I can tell you, I hinted at it, but that one has an easier solution because when you get done, you're going to get a positive, and it will be a natural log involving a sine or a cosine. So comes out a little nicer. So the last one we'll look at, you notice there's a little star there, because this one's a little bit tricky. And there's a couple of in the homework that are like this. So I'll just give you a little heads up on these. Number 47 in the homework and number 67 in the homework both have this feature where when you take the derivative of your u, it doesn't work out perfectly, but there's a way around it. But it is a little tricky if you haven't seen this before. So I'm going to show you this one so that when you see it after that, you'll kind of be aware of it. So with number 46, the kind of natural instinct here is to first notice that we don't have anything like this in the tables, right? In our sheet, our integration sheet, this is not on there. And remember, you can't like distribute this through a square root symbol or anything weird like that. So kind of the only thing we've really got is u-substitution. So at this point, you might just say, well, let's do u-substitution. Really, that's all we've got, right? So this is the inside function. That's kind of how we've done this. So u equals this thing. So then du equals, well, the derivative of 2 plus x is just 0 plus 1, right? It's just 1 dx. So du equals 1 dx or just dx, right? So sometimes this will happen. If you have a linear expression here and you take the derivative, you're just going to get a number. Like if this had been 2 plus 5x, we would get 5 dx. But because it's just 1x, we just get 1 dx or just dx. So what you'll notice is I can swap out the dx for the du. Let's just go ahead. Let's just start swapping this out. And you notice that I've got this x squared that's still here. This is u, and then we've got du. And this is not going to work. We can't have these mixed together like this. We can't have u's and x's. It's got to be all x's or all u's. So right here, you can see we're good here. This is the square root of u. dx is du. But what about this x squared? Well, sometimes what we have to do is go back here and figure out what x squared is. So go back to our original substitution. And if this is true, that would imply that x equals u minus 2, right? Looking at this, if I solve this for x, I subtract 2 from each side, and then I've got x squared. So if that's x squared is just going to be u minus 2 squared. And that's the way we can get out. That's the way we can get rid of this x squared and swap it out with something in terms of u. So this gives us u minus 2 squared times the square root of u du. So if we're going to integrate this one still isn't on our sheet, but this one now we could, if we wanted to, we could at least square this and distribute this through, right? So we can actually solve this one if we do that. So this one, if I square u minus 2, this is one last chance for you guys to do what you said you promised you would never do. You guys would never write that, right? U squared plus 4. Never, ever. Because remember, we have to take two of these things, two of these binomials, line them up and multiply them together, so we would never get this. So if we actually FOIL that, we'll get u squared minus 4u plus 4. And this square root of u I'm going to write as u to the 1/2. Because for us to actually do this problem, we're going to have to distribute this through here. Okay, so if we do that, I'll move it up here, we would get, this is equal to u, so we've got u squared times u to the 1/2. So it's like u to the 4 halves times u to the 1 half, so it's u to the 5 halves minus 4u to the 3 halves plus 4u to the 1 half du. So just verify that in your mind that it works. So I distribute u to the 1 half through here. Right, all these powers would increase because I've got 2 plus 1 half, right? 1 plus 1 half, and then this is just 4u to the 1 half. And then we just use the power rule a bunch of times. So we would get, for this one, this power goes up by 1, so 5 halves plus 2 halves is 7 halves. Divided by 7 halves is the same as multiplying by 2 sevenths. You get 2 sevenths u to the 7 halves minus 4 times, well, u to the 3 halves plus 1 is like 3 halves plus 2 halves, which is u to the 5 halves, and we have to multiply by 2/5, right? Because instead of dividing by 5 halves, we can multiply by 2/5. Then we have this 4, and we have u to the 1 half plus 1 is u to the 3 halves. So we, instead of dividing by 3 halves, we multiply by 2/3. And what do we have to put on the end of this no matter what? Plus c, right? It's an indeterminate integral, right? Indeterminate. It's not going to be a number. It's going to be a function plus c. Okay, so let's clean this up a little bit. Boy, this is getting a little messy here, but let's come back down over here. This will give us 2 sevenths u to the 7 halves minus 8/5 u to the 5 halves plus 8/3 u to the 3 halves plus c. Are we done? No, we're not done, right? We have to resubstitute our u. Remember what u really is? U is really just 2 plus x. So we have to plug in 2 plus x. We get 2 plus x to the 7 halves minus 8/5 2 plus x to the 5 halves plus 8/3 2 plus x to the 3 halves plus c. And that is our final answer for that problem. So give these a shot. As I mentioned before, integration is a really important topic for us, and for especially for you guys going on into any class that has calculus. So these take a little practice. Make sure you work on them pretty consistently and pretty hard, and let me know if you have any questions.